Hello and welcome to my presentation on stream ciphers. I'm going to be talking about how to implement a simple stream cipher in Python and the importance of pseudo-random number generators and the integrity of any sort of encryption algorithm. The format's going to be, I just have a couple slides to go through here, but most of the discussion is going to be in actually practicing in Excel, and then at the very end I'm going to spend some time showing you how to implement the algorithm in Python. Okay, so I like to think of a stream cipher as a zipper where the stream as it's being encrypted is the slider moving down the zipper, and the two pieces of data that are being XORed together or exclusive ORed together are the left and right chain of the zipper. Now, it doesn't necessarily have to be exclusive ORed, but most encryption algorithms at their core use exclusive OR, and I'll explain why eventually here. But we'll think of the left chain here as the plain text that you're encrypting and the right chain as the encryption key. Now, the encryption key could be a single number, or it could be a chain or sequence of numbers that are randomly generated or pseudo-randomly generated. The latter is better, and again, I'll explain why as we go on. So this is our flowchart for the algorithm. That circle with the cross in the middle is a symbol that represents our exclusive OR operator. And the two inputs are the plain text message, or it could be any other information. I'm going to show you how the experiment works with an image as well as plain text. And the other input is your pseudo-random number generator, and the one we'll be using is the middle square pseudo-random number generator. And the output is an encoded message. So exclusive OR. If you do a little research, you quickly find that most encryption algorithms rely heavily on exclusive OR. Why is that? Well, exclusive OR is just like the OR bitwise operator, except for this part of the truth table right here, where 0 or 1 results in 1, and 1 or 0 results in 1, but 1 and 1 results in 0. So it has to be either or, it cannot be both. And that is the characteristic that kind of makes this function or this operator interesting, because it doesn't leak information. So in other words, if I perform A and B exclusive OR, I will get an output, but I can't know what A or B was unless I have at least 2 out of the 3 pieces of information, right? If I have B in output, I can figure out A. If I have A in output, I can figure out B, and I'm going to demonstrate that here in a minute in Excel. Another interesting characteristic of exclusive OR that makes it useful for encryption is that it's an involutory function, which is a fancy way of saying you can reverse it. Mathematically, it's represented by this little function here, where f of x equals x. So in other words, if we take the output of the function and feed it back into the function, we will get the original input. And it's really fast. It's heavily optimized for machine code. So let's open up Excel, and I got some examples to show you. So again, here's the truth table. I went over that in the previous slide, but we're going to actually practice exclusive OR and see how it works. So here what I have is 2 imaginary bytes. I'm going to exclusive OR them together into an output, and then we're going to exclusive OR A and the output together, and it should reconstruct B. So 0 or 1 is 1. I'm sorry, 0 exclusive or 1 is 1. 1 exclusive or 1 is 0. 0 exclusive or 0 is 0. 0 exclusive or 0 is 0. 1 and 1 is 0. 1 and 1 is 0. 1 and 0 is 1. And 0 and 1 is 1. Okay, now we can see I just had this pre-populated with that information down here. So the output, if I take this and I XOR these two together, I should get B back out. So let's try that. 0 exclusive or 1 is 1. 1 exclusive or 0 is 1. 0, 0, 1, 1, 0, 1. So we can see right away that these match, and that's the expected results, right? If you can reverse it, it's involutory. Oh. So the exclusive OR operator alone will can be used to encrypt information with a given key. The key could be just the same integer or sequence of integers over and over and over again. But in a later example, I'm going to be able to show you exactly why that would be a poor encryption algorithm. So I'm going to talk a little bit about random numbers or pseudo-random numbers. So one of the earliest pseudo-random number methods or formulas was the middle square method, invented by John von Neumann in 1946. He's famously quoted for saying, "Anyone who considers arithmetical methods of producing random digits is of course in a state of sin." And the way I interpret that is he's basically he's mocking a little bit the fact that we're trying to yield random results from a system that is inherently deterministic. That is, arithmetic always produces the same results. It never produces random results. 5 plus 5 is always 10. It's never sometimes 11 or 12. It's just always, it's reproducible. So what we have is a term coined pseudo-random numbers. Now we know they're not random, but the patterns are indiscernible, and the periods in which they repeat are so vast that we as simple human beings really can't perceive the difference between them and an actual random number. So there's a lot of different ways to develop a pseudo-random number. This method here was chosen just because it's simple to explain and was really easy to implement, but I did also look into a couple other methods. This is not the fastest, but like I said, it's pretty simple. So the way the middle square method works is you have two parameters that you really need to think about. The first one is the number of digits that we're going to extract. We're going to call that the n number of digits. And we also need to select a random seed. Now your random seed is your starting value, and it's common almost at pretty much every pseudo number generator that I can think of requires a random seed to start with. And so the way it works is you take your seed value, you square it. From the square you extract the middle n digits, and then that value is your random number, but it's also your seed value for your next random value. So, like I said, that's pretty simple. It's really easy to implement in Python. Some of the limitations are the way I implemented it was the way that was most intuitive to me, was to convert the value to a text string. And then once you have it in a text string, you take a substring of the middle 5 digits or 10 digits or whatever you selected, which is inherently kind of slow. It's really not the best way to get a random number, to convert it to text first. Seems kind of dumb, but I was just doing it to quickly learn about it. And then another limitation of it is if you have a number where all of the middle digits are 0, then your output of the function is going to be 0, and you're going to feed 0 right back into the next iteration, and you're going to square 0, and then you're going to extract 0, and then you're going to feed 0 back into the next one. And so once it hits 0, the function's broken. Your output will just continue to be zeros forever, which I actually encountered when I was implementing this. So I intentionally chose values that I knew wouldn't come up upon a 0 for our little experiment I'm going to show you. But if you were seriously implementing this, you'd want to have a case for 0. Alright, so now we're going to talk about the actual code. For this project, you'll need Python 3.7. For the image processing part of this project, you'll need OpenCV and NumPy. Alright, so let's begin by writing our text encoding function. Now our text encoding function is going to take in 2 arguments. The first argument is going to be the message that we're encoding, and the second message is going to be a pointer to a function that returns the key string. Sorry, the keyboard was acting up there. Alright, there's our 2 arguments. It's going to return another text string, so we're going to initialize that to an empty string like that. Then we're going to iterate over every character in the message, apply our exclusive OR to it with the key string, and then return that result. So to extract the substring of just the character we're looking at right now, we'll use Python's string indexing. So at position I to I+1, we'll assign that value to char. Now to actually perform our exclusive OR operation on it, we need to convert this string into a numeric value in Python. So we're going to use that the ORD function, which is going to return the ASCII character code of that character. Okay, and then finally we can perform our XOR operation and append it to the result. And we're going to have to convert it to a char. I'll show you why. So that's going to be our integer value. That little caret means bitwise exclusive OR. And then we're going to XOR it with keystring. And at this point in time, we have an integer value that we're appending to a string value. So that won't work. We have to cast it to a char first. So that'll work. We can return the result. And right away, this will pretty much work out of the box if we pass it, you know, a function for the key stream. So let's try this. Let's set up equals hello world. Ciphering is fun. And I'm going to say encoded message equals encode text. We're going to pass it message. And then we're going to pass it a function that doesn't exist yet. I'm going to call it 42 because I've imagined, for the sake of testing some of this stuff, a random number generator that is so bad that it can only it can produce any random number as long as it's 42. And that's pretty neat. When we apply it to image processing, you'll see why later. And we're going to print the message. We're going to print the encoded message. And then we're going to want to make a decoded message from the encoded message. So because it's a symmetric key algorithm, we're going to just take the encoded message, pass it through the exact same function that we use to encode it, and pass it the same key, and we should get the original message, right? Just like we looked at in Excel when we were doing the XOR operation in there. It's the exact same thing. We should be getting the original message. Okay, now the only thing we're missing in order to test this, that wouldn't have worked, that would have caused an issue, is we need the 42 function. And that one's going to be a really interesting thing to implement, because that's how it's just going to return 42. Alright, I'm going to hit F5 to run it. And it popped over onto my other monitor, so I'll drag it over. So here's our first message. Here's the ciphertext that we created, and then finally here is the decoded message. So it worked just fine. Now this isn't a very good cipher, and it's probably not apparent why when it's just applied to one string, but when I show it on an image later, you're gonna totally understand why. So let's implement our middle square method that we talked about earlier. So in order to do that, I'm going to first make a utility function to extract the middle substring of a string. So let's go ahead and do that. We're going to call it extract middle. It's going to take two arguments, text and digits, where digits is the number of characters we want to extract, and text is the source text that we're extracting it from. So similar to what we did up here with the string indexing that Python has for getting a substring out, the difference is going to be, it's not going to be I and I plus 1. We're going to have a left character position and a right character position, and we're going to calculate those based on the width of the text string minus these digits divided by 2. So width equals len of text, right? And so our left position is going to be width minus digits divided by 2. Now that could return a decimal or floating point, and that will break later when we go to do string indexing. So we gotta cast this to an integer, which is actually just going to truncate and throw away anything after the decimal point. Then our right position is going to be as simple as saying left position plus digits. And then we're going to return the substring, which is going to be so we can test this. We'll do print extract middle abracadabra, and we'll extract 5 digits and run it. Gives us a kata, which that is the expected results, because it's 3 characters of padding on either side, 5 in the middle. Now to implement our middle square algorithm. Like I said, we're going to have two parameters here to think about. We need the seed value, which we're going to start at 1, 2, 3, 4 in digits. We're going to start with 5, and middle square pseudo random number generator. Doesn't take in any arguments because it's using globals. Now, I normally hate using global variables, but we are doing it for the sake of demonstration here, not for actually writing usable code. So like I said, the first thing we do is we take the seed and we square it. Then we're going to extract, think about it, we have to convert it to a string first, then we have to extract the middle, then we have to convert it back into an integer. That's why this isn't the most efficient way to implement this, but whatever. So middle string equals extract middle string of seed, and digits is our global variable, so we can change it later if we want. So if we have the middle string, I can say the seed is going to be that string converted back into an integer, and then we're going to return the seed. Alright, now let's just let's generate 100 values and see what it looks like. Yeah. So some of these aren't 5-digit numbers, and that's okay. It should be any number up to 5 digits. And immediately you can kind of see that it's working. None of these values look like they have a pattern to it. So this isn't useful in the current state. What we really want to do is we want to normalize these values to a number between 0 and 1 so that we can scale it to whatever size we want. Because in the end, when I'm going to encode this message, I need byte values, so I need numbers between 0 and 255. So to normalize it, all we have to do is we have to divide it by the maximum. We have to divide the output of this function by the maximum value that it could ever return, which is going to be 10 to the 5th power, right? Because it's 5 digits. So I'm going to say normalized PRNG is what we'll call it for now, and we're going to return middle square PRNG divided by 10 to the digits power. I'm going to put global digits in here, even though it should know I'm talking about the global scope since that's the only digits I have. And then all we'll do is we'll change our little output here to normalized output and see what we get. Okay, so here we have a lot of floating points. Looks like the highest number I see, you got like a 0.94 there, 0.95, 0.98. There we go. And you got a 0.037. So it looks like it's working. We have all kinds of values distributed between 0 and 1. Now, in order to make this usable for the next part, we need that to be scaled between 0 and 255. So I'm going to make a function called random byte. And for this, all we're going to do is return normalized PRNG multiplied by 255, because that'll give us a value between 0 and 255 now. But that's going to have decimal points, which means it will be way more than a byte. So we're going to convert it to an int, like that. And then we'll run this test program again, now looking at random bytes. And so that does the expected result. We have a byte value of 4. Yep. we have the whole gamut of bytes. Alright, so now we're really close to having a pretty decent encryption algorithm. So let's try another message. This is more secure as the message. We're going to print the message. We're going to encoded message equals encode text message, and we're going to pass it the function pointer random byte this time. And now what's interesting is, in order to decode it, we're going to have to reset the seed. If we don't, it's going to be decoding with a different stream of random numbers than it encoded with. So let's here set the seed back to 1, 2, 3, 4, and then say decoded message equals encode text. Now I know I should have named this something better because it can be used to both encode and decode, but you get the point. Encoded message is going to be the input parameter to this one, and random byte is still the same function. So now here we'll print all of our messages. Run it. The errors, the most common errors are just the typos, right? Okay. This is more secure. That's our input message. This jarbled up text is our encrypted message, and then this is it decoded again. I'm going to comment out the resetting of the seed so that you can see that it won't work without the right seed. So there's the input message, there's our ciphertext, and this is when we attempted to decode the message without resetting the seed. So just garbage. Alright, so this concludes all of the plain text version of this. The next thing I want to look at and show you guys, because it's really interesting and it's a very intuitive way to understand why some algorithms are more secure than others, is we're going to apply this to an image. So we can get rid of this. What you need is we need OpenCV and we need NumPy. So those are, if you install OpenCV, you'll automatically get NumPy because NumPy is a dependency of OpenCV. So anyway, go ahead and import these two. Now let's just start by displaying an image, right? So that'll be the first step towards encrypting an image, is loading an image and showing it, which is super easy with OpenCV. We're just going to do OpenCV, or source equals cv2.imread, and then in the working directory of this script I have a file called grayscale.png, and I'm going to do cv2.imshow. We're going to call the window original. I'm going to show, and the image is, I think, basically just a NumPy array. And if I hit run, you should see it. And there she is. That's my daughter. Now I did some work to this image to make it easy to encrypt. First of all, I made it grayscale, so there's just one channel of bytes to encrypt. There's no reason why you couldn't do, RGB and do 3 channels, or however many channels you wanted you could encrypt, but just to keep it simple, we're doing one grayscale channel. So each of these pixels is a value between 0 and 255. That's really similar to our text stream, right? You can imagine encode text, this function here almost works for an image if it was like a one-dimensional image, but it's not. It's a two-dimensional image, so we could either like convert the two-dimensional image to a one-dimensional thing and then pass it into here, or we could just rewrite this to deal with 2 dimensions of information, and that's really not that hard to do. So let's just do that. Make another function called encode image, source image, and key stream. Still, it needs those 2 functions still, or those 2 parameters still. And we're going to grab the size of the image, and then we're going to iterate over the rows and columns and do the same thing. So first thing we got to do is initialize a numpy array of the same size as the input image. So we're going to call numpy zeros, which generates an array of zeros to any size you want and of any data type you want. We need to have the same shape as the source image shape. I believe the shape's just a tuple, so it's going to be 2 values, a width and a height. And the data type is going to be np.uint8. It's very important that you do that. If you don't, it won't work. If this is like a floating point or a double or something like that, it's not going to work. Alright, so now we have our output image initialized. We're going to return result image, and then we're gonna do our computation here. So we have to iterate over every row and column. So remember, I said this is a tuple with 2 values, so we're going to iterate over all values between 0 and the width, which is stored in the first value of the tuple, or the 0 index. And then we're going to iterate over the second value of the shape index. Again, this is just the width and the height of the image in pixels. And by second, I mean the first index. Okay, and then we're going to reference those pixels ij of the resulting image and set it to equal to the source image ij. Now if I stop right here, I've just written a really inefficient way to copy an image from one spot in the memory to another. That's not what we want to do. We actually want to do some work to it. So there's the work, the exclusive OR algorithm, or the exclusive OR operator, and the key stream function that we're passing to it. So let's take our source image, and I want to encode it with our fancy 42 key stream. So what that's going to do is every pixel in the image is going to be XORed with the number 42. And it's going to make it immediately obvious why that's a bad idea to use for encryption. And random byte. No, I'm sorry, 42, right? Well, I meant to type J there. That was my mistake. So here's our 2 images. Here's the original and here's the encoded one. This is distorted, but you can still make out the contours. You can tell the basics of what the image is. Like, you can see my bazooki is right there. You can tell that that's a human being. This isn't terribly well encrypted. And if you think it's because there's something magical about 42, I just chose the wrong number. Well, let's go ahead and close these and choose a different value. Let's try, I'm 35, so let's choose 35. Okay, so the problem is the XOR returns a different image, but it's a very predictable image. So anybody could probably reconstruct the original image without too much work, right? Because there's a total of 255 keys I'd have to try before I found this one. Let's change one thing. Let's change our random our key stream to random byte. So then the key of the encryption algorithm becomes the seed of this function. Oh, my bad. Need to pass random byte into that function. I'm surprised it even let me do that. Alright, here we go. So here's our original image again, and here's the encoded image. Now if you look carefully, you can still see these patterns. And the problem is middle square is generating some random numbers, but the period isn't big enough to go over the entire image, so there's some repeating values here, and that's why we see all of these patterns. Now one quick and easy way to fix this is to simply increase the number of digits here that we allow the function to generate. So let's change this to 15 digits, and let's change the seed to 1, 2, 3, 4, 5, 6, 7, 8, 9. Now it looks like noise, right? You can't see any semblance of the original image in there, and this is a good analog for talking about how good an encryption algorithm is compared to other ones. This one would be much harder to crack than the other one. Visually, you can immediately tell the information is more encrypted. So that's it. That concludes my video here. I hope you guys enjoyed it. I hope you learned something from it, and I hope I get a good grade on the course. So thanks for watching.